to this point, we've been discussing ideal gases, but not all gases behave exactly ideally. Real gases behave a little bit differently from ideal gases. Our ideal gas laws assume no attraction between gas molecules, and the gas molecules don't take up any space themselves. At low temperatures and high pressures, these assumptions aren't exactly valid, though the difference isn't really that much. You can see here that our molar volume is 22.4 liters per mole for an ideal gas. For chlorine, we see that it's 22.06 liters. For carbon dioxide, it's 22.31 liters, and this is at STP. For ammonia, 22.4, so that one's pretty close. Nitrogen also 22.4, helium 22.41, and hydrogen 22.42. So there's a slight variation. At low pressures, the molar volume of argon is nearly identical to that of an ideal gas. But as the pressure increases, the molar volume becomes greater than that of an ideal gas. In other words, the particles themselves begin to take up space, or effectively begin to take up space. At the higher pressures, the argon atoms themselves occupy a significant portion of the gas volume, making the actual volume greater than that predicted by the ideal gas law. So you can see here that at high pressures, the volume is higher than what would be predicted of an ideal gas. That's because the molecules actually do take up space, and their actual size begins to become important at high pressure. So we have a modification to the ideal gas equation that are a couple of different constants that help us account for this. So we can solve the ideal gas equation where volume is equal to nRT over P, but we can add a constant according to whatever gas we have to correct for this deviation from ideal gas behavior. So our B is our van der Waals constant, and it's different for each gas because the molecules are different. So our ideal gas equation with a correction for their actual size of the gas particles is V equals nRT over P plus NB. Now at high temperatures, instead of pressure, the pressures of the gases are nearly identical to that of an ideal gas. But at lower temperatures, the pressures are less than an ideal gas. So at lower temperatures, the gas atoms spend more time interacting with each other. In other words, they get a little bit sticky. They spend less time colliding with the walls of the container, and this actually reduces the pressure relative to an ideal gas. So at low pressure, the effect of intermolecular attractions becomes significant. And we have a correction factor for that as well. So A is another van der Waals constant that we can use for each gas to correct for the lower pressure at low temperature. So if we solve for P with the ideal gas equation, we see that it's nRT over V. So we have a correction for a non-ideal gas behavior at low temperature. So P is equal to nRT over V minus A times N over V squared. So we can combine these to get a more accurate representation of non-ideal behavior of a gas. So we have a correction for intermolecular forces and a correction for particle volume. So this is our new equation, our van der Waals equation for non-ideal behavior, and this is called for real gases. So P plus A times N over V squared times V minus NB equals nRT. And that's our correction for particle volume and our correction for intermolecular forces. Now we only use this equation when dealing with real gases. And the Trow book doesn't actually have any calculations with this equation. We're just giving it to you now to demonstrate when it would be used. Now if you take physical chemistry, you'll use this equation to calculate data for real gases. If you plot PV over RT, versus P on a graph for 1 mole of a gas, you can show the difference between real and ideal gases. It reveals a curve that shows the PV over RT ratio for a real gas is lower than for an ideal gas for low pressures, meaning that the most important factor is the intermolecular interactions. And it also reveals a curve that shows the PV over RT ratio for a real gas is higher than ideal at high pressure, meaning the most important factor there is the molecular volume. So you can see pressure versus PV over RT for a real gas. And here we have an ideal gas at 1, okay? And we see the deviations of the other gases. This graph shows PV is greater than RT for carbon dioxide at 3 different temperatures. Rank the curves in order of increasing temperature, A versus B versus C. And here we can see that C would be less than B would be less than A.